Hello again, this is Aaron Jerome Electronics, and we are at State Machines Part 6. This is the practice problem that I give my students to work on, but I help them through it, and then after this I probably wouldn't do another video, but I might just give them a problem to work on after this one, and that doesn't matter to this video, so we're going to go through the student practice problem now. This is the worksheet that I give to the students. They complete all of this, they hand it in, and, if all the work's done, then they're going to go to Multisim and simulate it. So here we go. Well, one thing I should probably mention is in the past, we have built a Mealy machine, then did the waveform analysis of the Mealy machine. I introduced state machines. We've gone through a complete Moore version and shown you the differences. We've practiced our way through that, and here we are doing the student work. So the practice problem will be a Moore machine, not a Mealy. I like the Moore machine better. So the objective here is we're going to design a machine that doesn't find a sequence. This time what we're going to use is a 7-segment display, and we're going to have a single 7-segment display flash the letters O, P, E, N repeatedly. And we're going to set it so that we have two controls on this. One is going to force it to start at 0, and the other control will stop it at any letter as long as we just push either of these buttons. Now, there's easy ways to do this and hard ways to do this. Well, there's intuitive easy ways to do this and correct ways to do this, I should probably say. So I'm going to be doing it the correct way, but I've seen in the past some instructors, I have to say, there was a long time that I didn't completely understand state machines. I guess I do now, but I've seen instructors that didn't get it and just gave their students some shortcuts, and I think it's better that they understand this much. So anyway, moving on, this is the first step. The first step is to think. And in this thinking phase, you need to figure out the current state register and how many flip-flops it needs. So if we are going to use a Moore state machine, and we're going to have the word open spelled, open uses 4 letters, that's 4 states, but remember, Moore liked to use a 5th state. So how many states do we need for this machine? 1 for each letter and 1 for a blank state at the beginning. So the Moore version uses 1 state, one state for each letter, plus 1 more, an initial blank status. And so how many flip-flops do we need? Well, 1 gives us 2 states, 0 and 1, and every time we add a flip-flop, it doubles the amount of available states. So there's another flip-flop, so that will give us a total of 4 states. We can count all the way from 0 to 3, and that's not enough because we need 5 states. So here is the third flip-flop. That counts from 0 to 7. We have a total of 8 states. We need 5. 3 of them will be don't cares, if you remember. So we're going to combine these into our CSR. It's kind of interesting that we build the CSR very first, even before we have written down the state transition graph, the bubble graph. So that's where we're starting. So step 2 is to capture the idea as a state bubble graph. So putting 5 states here, counting 0, 1, 2, 3, 4 in binary, putting lines below them because it's a Moore machine, and the input goes on the transition arrow. This time there's only a single input. That's important. Before, the inputs were a continuous stream of numbers, input different numbers over and over again. There were only 2 numbers, but different numbers sent into the machine. This time, the input will be controlled by U, or we can give the control of that to another state machine in the computer and make, we can nest all these state machines, make a really smart machine like a vending machine. But the input here, we're just going to use a switch that will decide if the switch is set at a high or a 1, it will continue O-P-E-N, spelling O-P-E-N over and over again. If it's low, that will cause it to pause on whatever letter it's currently showing and continue to show that letter. And then we're going to also add another switch that will force it to start over at the letter O. So either 0 for disable will stop the cycle, 1 for enable will resume the cycle, and each input will be a 1 for normal operation. So for normal operation, we're putting 1s on the transition graphs that go from nothing to O to P to E to N in each one of the states. And then at the last state, if we get a 1, we're just going to start over and just repeat the cycle over and over again. If we get, well, I guess what we do is now we consider what happens if we get zeros then. What if we flip the switch, the input switch to the other direction and get a 0? Well, if you remember, what that means is we're just going to stop at the state that we got a 0 on. That means for each one of these, it's just going to stop. If we hit that switch and give it a 0, turn the switch off, make it a low, then it's just going to pause, continuing to show that letter. Not turn off, but continue to show that letter, which is why the attention of the computer is just going to cycle back to that particular state. Okay. Thinking about this graph, one wonders if an initial blank state is needed. Well, yeah, it's kind of nice when you're spelling the word open and you have a blank before the first letter, because that kind of tells you a word is going to be begun. However, I want to make this easier. If we take off the first state, of course, you know, even though Moore came up with the general idea, we can tweak it if we want. So I'm going to eliminate that first state because it's going to reduce the number of flip-flops from 3 to 2. That'll reduce the complexity of the circuit, but those are the benefits. There's also a cost, though. The blank output will go away on the 7-segment display. And so if you're not paying attention, it's supposed to say O-P-E-N, but if you catch it at, say, letter N, it'll actually look like it's spelling the word nope. So, that's the cost of what we're doing, of making it simpler. But I think this first worksheet probably, it's okay to make it simpler. We'll go harder later on. And so what would that look like? Well, that just means we're, taking off that first state. Now, there is our CSR. That means it only needs 2 flip-flops to be fed, and we're going to proceed with this model. The output is going to be not 1s if we're successful and 0s if we're not. This time the output is going to be letters O, P, E, and N. And so we're also going to add a reset control, and it will invoke the clear inputs on the flip-flop. You remember the presets and the clears. So we're going to invoke the clear inputs to force it to start at the first state, and that will be what we call the reset. Okay, so there's our state graph, and if you want to pause the video now because you already know how to populate inputs on truth tables, we do have an input here. So step 3 is to convert the state bubble graph to a truth table. And the inputs are going to be enable and CSS. So E for enable, and that's going to be a single digit. And CSS, well, we have 2 flip-flops to feed, and so we're going to need 2 signals for that, 1 for each flip-flop. Inputs are just a binary count. You know that. And I'm not even going to use E yet, just going to vertically binary count. The first column is the 1s column, so it changes every other 1 vertically. And the next column is the 2s column, and it changes every 2 vertically. And then the enable is a single bit, and that's going to be the 4s column, so that's going to change every 4. And now we have all the inputs. We've considered every possible combination of these 3 inputs. All right, so we're going to figure out the next states now because that's the next step, to figure out the next states. And we're going to have to figure out what NS0 is, next state 0 and next state 1. And to figure out these next states, we do what we usually do. Here it says we're in state 0, and we get a 0. Next state, 0. So stop the video, populate the rest of this, and come back, see if you got the same thing I did. I'm pausing, and now I'm continuing. All right, so if we're in state 1 and we get a 0, that just goes back. If we're in, so it's the same, next state is the same state as long as we're getting zeros, right? Next state, if we're in state 2 and get a 0, we're going back to state 2. If we're in state 3 and get a 0, we're going back to state 3. Now we're doing it all over again with 1s. Okay, if we're in state 0 and get a 1, we're moving to the next state. If we're in state 1 and get a 1, we're moving to the next state. If we're in state 1, or no, if we're in state 2 and get a 1, we're moving to the next state. And if we're in state 3 and get a 1, we're moving to the next state. There's no don't care wildcards here because we're using all of the states provided by 2 flip-flops. Okay, so the other outputs are going to be used to paint or to control a 7-segment display. And if you remember, and I probably should have changed this video to do this at the beginning, but we don't need, on the Moore state machine, we don't put these inputs from, the outside. Those are not fed into the output decoder, so really we only need to do 4 of these 8 rows because we're spelling the word open. And of course, if we go back to O, it'll stay in O, and if we go back to P, it'll stay in E. But I'm going to do it the long way because that's what I designed. So we are taking our outputs to the segment drivers. What that means is if we're in state 0 and we want the 7-segment display to be a 0, you can see we need every segment except G on the side there, A, B, C, D, E, and F. Now, hopefully you're ready to move ahead and do all this because we've done assignments that do this before. You know how to do this, so I suggest you pause the video and work ahead of me and see if you can fill out the entire truth table. It's just going to be the letters that paint the 7-segment display for the letter you want. Pausing now. Okay, here we go. So if we're in state 1, we want to spell the letter P. And that means we're going to need A, B, E, F, and G. And for E, we don't need B and C, so we're going to need A, D, E, F, and G. And then for the last letter, this kind of throws students for a loop, but I like a tall N here because a short N isn't as tall as the rest of the letters, and it looks actually weirder if it's short. So I'm going to make a tall N here, and that just means maybe you need to erase this and do it again. But for a tall N, we need A, B, C, E, and F. And then we're just going to do it again down below because if we get 1s, well, here I am saying we don't need that input call, or we don't need the inputs at the output decoder. So all of this we're not going to need anyway, but it's just a repeat if we get 1s. Okay, so we'll only need 4, but I'm just repeating again. Probably could just eliminate these because we don't need them, but if we have a full truth table like this, NSS requires 8 rows. And the outputs for the 7-segment display, they only need 4 rows. So now we're going to do some simplification. We're going to start by simplifying the NSS. This might be another place where you stop the video and try to work ahead of me, proving to yourself that you get this. Or maybe you want to just try to work slightly ahead of me and pause to listen to what I say if you get stuck somewhere. But you should know this. You've been doing a lot of K-maps, and so here we go. I do want to make sure that this K-map, I populate it horizontally, which means I'm going to put the E on the side. Now we have 3 input columns, which is why we have 8 rows here. But I'm going to make sure that the enable is underneath the tail. I'm going to simplify for NS1 first. There's the double not, left not, no not, right not, and the 0 and the 1 for the enable. And I'm just populating the K-map rather rapidly And hopefully this is what you got as well. So now I'm going to begin implicating ones, and I think I'll start with these two. Over on the left side, we can't cancel against that 0, so we're going to have to keep a not e as part of NS1's solution equation. Above, the digit on the right, 1 is a 0 and 1 is a 1, and that represents the variable on the right, CS0, that cancels out. Keeping the not e, those two cancel out. And of course, we're keeping the CS1 because they're not opposites. And there is the first implication. And remember, within implications, we multiply, and between implications, we add. The next implication I'm going to do is this one. These two ones cancel everything out on the side. That cancels out E, but we have to keep both CS1 and not CS0. We're going to add that to the first implication, canceling those out, adding those two, and now we've got 1 left. That's kind of cantankerous because we can't cancel anything. We have to keep not CS1 times CS0 times E. So there's E times not CS1 times CS0. But now we have the whole thing done, and there is our simplification. So next, I'm going to use the same K-map for NS0. I think I put 2 of them on your paper. So NS0 is formatted the same way, and now I'm going to populate it. We've done this so many times, hopefully I can do it quickly now, and you're okay with that. Notice in the upper row, we have 2 1s together that we can implicate. And that means we're keeping E for enable, but it's a not E because it's a 0. And then above, the values on the left are 1 and 0. They cancel out. That means CS1 will not be used. But the values on the right are both 1s. That means CS0 will be used. And canceling out those, we don't need those. We got the 2 1s on the bottom. We can cross the borders of the K-map and combine those, and that makes simplification easier. We're definitely going to be using E in our solution, adding this implication to the previous implication. Above, looking for opposites, looks like we've got opposites 1 and 0 on the left side, so CS1 will not be used, but same's on the right side, so CS0 will be knotted and it will be used. CS1 will be canceled out and not used because they're opposites. And now we have the 2 next state signal equations. And we only needed those 2 equations. So now the last 4 rows here are just repeats of the first 4 rows. We don't need them for the output decoders because we don't send the input signal to the output decoders because E it doesn't change the letter display. That's what it's saying. So if we're here, if we're in this state, we're displaying this letter. If we go back to this state, we're also displaying this letter, and that's really what's being said there. So the K-map only needs, for simplification, we only need the 4 rows, and so we're simplifying those, and that makes little 4-square K-maps. So anyway, we're putting CS0 on the top and CS1 below, and notice that CS1 is now the first variable on the first input because we should have eliminated the enable column because we're not using it here. And so that means I'm horizontally populating this K-map. And it looks like we got 1s everywhere. What does that mean? That means A is always used. A will always be on. Okay? And if you look at the K-map, you can see also that that will be the case for segment E, it will always be on, and segment F, it will always be on. But for segment B, we put 3 1s in, and they're like this. We're going to have to implicate these 2. That means we're going to be canceling out CS0, but keeping not CS1. And then we're going to add to that this implication where CS1 is canceled out and we're keeping CS0. And that's B. If you notice on your worksheet over on the right side of the truth tables, I think, is a place to summarize all of these K-maps, so you have an easy place to find what you need up there. That's why I put that there. You can use it if you want, don't have to if you don't want to. C has 2 1s, but they're in opposite corners, so that means we can't really simplify. We have to use everything. Not CS0 and not CS1 plus CS0 and CS1. There is our summary. You can pause at any time if you need me to go slower, but I'm going to keep going. Here is the K-map for the D. It has 2 1s in it, and they're in very convenient places, and so we implicate them together, canceling out CS1, but keeping not CS0 done with D. As stated before, E is everything is on, that's a 1, and F, everything is on, and that's a 1, and G. G is in opposite corners again, so we're going to have to implicate them separately. So we're going to have to say not CS1 and CS0 plus CS1 and not CS0. Okay, so there's G. So we don't need the truth table. We don't need the state transition graph anymore. Everything here is encoded into the equations. So we've extracted everything we need from the original idea. It's all in the equations now. And our state decoder drivers are here. Next state decoder drivers are here. So we don't need the truth table. And now we can start constructing our state machine. This is the format of the state machine. But my students have made so many simulations before that this is easy for them, but this is also time consuming. So I went in and built this much, and I give them a copy of this for the template. So all they have to do is hook up the logic in their simulation when they go to multisim. So they've already got this, and I'm getting you started by making the NSD first. This is, of course, the CSR, and the output decoder will be over here. And I'm going to start by making the NS0 and just kind of explaining what things are, and then I'll leave you to it. You can start hooking things up, but I need to make a few explanations. First of all, this is the enable key. What that does is stops the progression of the word at a letter. And so we will need that. And I have made an is version of the E, and I have made a not version of E that you can hook up on the bus here, and they're labeled. I don't know if they're labeled on your paper, but maybe they are. If they're not, they should be, and I might do that in the future. Okay, so we're going to need a copy of not E, right? And there's the not for E, and there's the not line for E, and I don't have to use the not gate now. I can just plug it into the AND gate. I'm going to multiply that with CS0, and that happens to be right there according to the label. And then I'm going to add that, so I'm going to need an OR gate. I'm going to add that to a copy of regular is E, not E, and I'm going to multiply that by not CS0, plugging that in there. I can plug that into NS0, and I've got that logic completed. I'm going to have you do NS1 on your own down below. This is the space to do it. Don't forget to use triple or quadruple or double input gates as needed. And also we need to talk about the 7-segment display side. I'm surprised that when I don't explain what I'm about to explain, students do some funny things. But I had one student, they thought, well, all these 3 1s, they're just 1s. They need to be on all the time. So they made an extra wire that follows the wire below it here, not realizing that they were just being redundant, and they plugged it into the VCC. Well, that's what this wire is. This signal, it plugs into a 1. The VCC voltage 5 volts, that's a 1. So you can actually, and you don't have to plug into this wire 3 times. You can take one wire over here and plug in A and E and F, and you've got all 3 of these done. Next, you're going to plug D into not CSO, That's what this open space here is for, is to make your logic, because this open space is for the output decoder logic. So you're going to build B, C, D, and G down in this space down here on your machines. So that's, I think, as far as it goes with this. I do go a little further, though, because I like to have you figure it out from here. But there are some other, let's see, I think I said all this. There are some other things I want to say. This is a state machine that simply repeats numbers 6491 for just some crazy reason. And of course it does that, but state machines can be connected to candy bars or pictures or cash input, coin input, card input, or pictures that could be called animations. And so state machines can drive all kinds of things, and that's what I wanted to point out here. So state machines work well for displaying stored information. They work well for analyzing input information. We've discovered sequences of numbers. You can discover coin combinations. You can discover all kinds of things on one end and tell it what to do and give it outputs. These are controllers. We've done some simple ones. And so that's basically, that is the end of all of the state machine videos. Hopefully this has made a lot of sense. I appreciate you watching it this far. If nothing else, these are really good if you lay down at night and can't sleep. Just watch some of these videos. They'll put you right out. But if you're really sincerely trying to learn this stuff, I'm hoping it will help, and hoping it has helped. And so please send me messages for how I can improve if you feel so inclined, because I know I make mistakes, and I always learn from other people, and I can handle, my ego can handle being wrong, which is why I do these videos. I don't mind being wrong. I think I'm the wrongest in the video that I did for what is it? Transistors to gates. I still think I've got a few things to learn about transistors. So watch that one and let me know where I can make improvements on that as well. I might want to just suggest here before I go that the next thing we're going to do, the next set of videos that I have prepared, and I think they're pretty much ready, I just got to find time to record them, 7 different videos that talk about the simplified equations. What industry is really doing these days is just slamming them into a programmable chip and then wiring that up as the prototype, which saves a lot of time. But to be able to do that efficiently, you need to understand how to program a programmable chip. And we do that with an application called Vivado. And the 7 video, I think it's 7 video segments that go through that. The first one tells you how to install Vivado for free on your computer. It can take a lot of space, but I think we've trimmed that down a little bit too. And then we're going to build something called a comparator in that. And so if you're interested in going, this will be the final grouping in my year. In future years, I plan to go even further than these videos and make new videos. But we are going to go into Vivado and use VHDL. We don't use Verilog in this class, but I've been told if you understand VHDL, you will understand Verilog quite easily. So so when I get back on, I'll be talking all about VHDL and how to use it to make a comparator. Anyway, this is Aaron Jerome, Jerome Electronics. Thank you for holding out this long. Hopefully you've had a good rest if you fell asleep, and I'll see you on the next video. Bye-bye.